Hello, my dears, and welcome to our astronomy course. Today, we are going to continuing study stars. The topics called the family of stars. I hope you notice in the HR diagram how the artist has used color to represent temperature. I want to remember in you last lecture now. Okay? So the HR diagram is a graph with luminosity on the vertical axis and temperature on the horizontal axis. A star is represented by a point on the graph that marks its luminosity and temperature. The HR diagram in this figure also contains a scale of spectral type across the top. Because a star's spectral type is determined by its temperature. And you could use either spectral type or temperature on the horizontal axis. In HR diagram, the location of a point tells you a great deal about the star it represents. Points near the top of the diagram represents very luminous stars, and points near the bottom represent very low luminosity star. Also, points near the right edge of the diagram represent very cool stars. And points near the left edge of the diagram represent very hot stars. Astronomers use the HR diagrams so often that they usually skip the words, the point that represents the star. In this figure, the main sequence is represented by a curved line with dots for stars plotted along it. As you might expect, the hot main sequence stars are more luminous than the cool main sequence stars. And notice in the HR diagram that some cool stars lie above the main sequence. Also, they are cool, they are luminous, and very little surface area from which to radiate, and that limits them to low luminosities. The equation in reasoning with numbers here can be used to draw precise lines of constant radius across the HR diagram. And these lines slope down and to the right across the diagram because cooler stars are fainter than hotter stars at the same size. Are you agree with me? Nice. And this figure plots the luminosities and temperatures of a number of well-known stars along with lines of constant radius. For example, locate the line labeled 1R with symbol Sun, square with dot in the middle, 1 solar radius, and notice that it passes through the point represented the Sun. Any star whose point is located along this line has a radius equal to that of the Sun. Next, look to the rest of the stars along the main sequence. They range from the 10th size of the Sun to about 10 times as large. Even though the main sequence slopes dramatically down, to the right across the diagram. Most main sequence stars are similar in size. In contrast, the white dwarf at the lower left of the diagram are extremely small, only about the size of our planet Earth. And the giants and supergiants at the upper right are extremely large compared to the stars of the main sequence. Notice the great range of sizes among stars. The largest stars are 100,000 times larger than the tiny white dwarf. If the sun were a tennis ball, suppose, the white dwarf would be grains of sand, and the largest supergiants would be as big as football field. Let's see at this figure, please, to compare the star's size. A star spectrum contains clues as to whether it is a main sequence star, a giant, or a supergiant. The larger a star is, the less dense its atmosphere is, and that can affect the width of spectral lines. If the atoms that produce these lines collide often in a dense gas, their energy levels become distorted and their spectral lines broaden. Hydrogen-Balmer lines are an example. In the spectrum of a main sequence star, the Balmer lines are broad because the star's atmosphere is dense and the hydrogen atoms collide often. In the spectrum of a giant star, the lines are narrower. Let's look at this figure, please. Because the giant star's atmosphere is less dense and the hydrogen atoms collide less often. In the spectrum of a supergiant star, the Balmer lines are very narrow. You can look at a star spectrum and tell roughly how big it is. Size categories derived from the spectra are called luminosity classes because the size of the star is a dominating factor in determining luminosity. Supergiants, for example, are very luminous because they are very, very large. The luminosity classes are represented by the Roman numerals 1 through 5, with supergiants further subdivided into types of 1a and 1b as follows. Look at the luminosity classes. 1a, bright supergiant. 1b, supergiant. 2, bright giant. 3, giant. 4, subgiant. 5, main sequence star. You can distinguish between the bright supergiants, 1a class, such as Rigel, and the regular supergiants, 1b class, such as Polaris or our North Star. The star Adara is a bright giant, class 2. Aldebaran is a giant, class 3, and Altair is a subgiant, class 4. Sirius and Vega, like the Sun, are main sequence stars, 5 class. When you describe a star, its luminosity class appears after the spectral type, as in G2, 5 for the Sun. White dwarfs don't enter into this classification because their spectra are peculiar. But notice that some of our favorite stars are unusual. Next time you look at Polaris, remind yourself that it is a supergiant. The positions of the luminosity classes on the HR diagram are shown in this figure. Remember that these are rather broad classification and that the lines of the diagram are only approximate. A star of luminosity class 3 may lie slightly above or below the line labeled 3. A scale of absolute magnitude has been added to the right edge of this HR diagram for easy to reference simply. Luminosity classification is subtle and not too accurate, but it is important in modern astronomy. As you will see in the next part of our lectures, luminosity classification provides a way to estimate the distance to stars that are too far away to have measurable parallax. Astronomy can measure the stellar parallax of nearby stars, but most stars are too distant to have measurable parallax. Astronomers can estimate the distance to these stars by the process called spectroscopic parallax, the estimation of the distance to a star from its spectral type, luminosity class, and apparent magnitude. Spectroscopic parallax is not an actual measure of parallax, but it does tell you the distance to the star. Spectroscopic parallax relies on the location of the star in the HR diagram. If you record the spectrum of a star, you can determine its spectral class, and that tells you about its horizontal location in the HR diagram. You can also determine its luminosity class by looking at the width of its spectral lines, and that tells you the star's vertical location in the diagram. Once you plot the point that represents the star in the HR diagram, you can read of its absolute magnitude. As you have learned earlier in our lecture, you can find the distance to a star by comparing its apparent and absolute magnitudes. For example, our favorite star, Betelgeuse, is classified M2 1A class, and its apparent magnitude is about 0.05. You can plot this star in HR diagram, such as in this figure, where you would find that it should have an absolute magnitude of about minus 7.2. Using the apparent and absolute magnitudes, you can then find the distance using the equation from previous lecture. Spectroscopic parallax places Betelgeuse about 360 parsec from Earth. More accurate measurements made by Hipparcos satellite reveal the distance to be 520 parsec. So the result derived from the spectroscopic parallax is only approximate. Obviously, a direct measurement of the parallax is better, but for more distant stars, spectroscopic parallax is often the only way to find their distance. What evidence can you give those giant stars are bigger than the Sun? Scientific arguments are based on evidence, so you need to proceed step by step here. Stars exist that have the same spectral type as the Sun, but are clearly more luminous. Are you agree with me? Okay, let's go on. Capella, for example, is a J star with an absolute magnitude of 0. Because it is a J star. It must have about the same temperature as the Sun, but its absolute magnitude is almost 5 magnitudes brighter than that of the Sun. A magnitude difference of 5 magnitudes corresponds to an intensity ratio of 100, so Capella must be about 100 times more luminous than the Sun. If it has the same surface temperature as the Sun, but is 100 times more luminous, then it must have a surface area 100 times greater than that of the Sun. Okay? Because the surface area of a sphere is proportional to the square of the radius, and Capella must be 10 times larger in radius. That is clear observational evidence that Capella is a giant star. In this figure, you can see that Procyon b is a white dwarf, slightly warmer than the Sun, but about 10 times less luminous. Build a scientific argument based on evidence to resolve this question. Why do astronomers conclude that white dwarf must be small stars? Try to find your explanation, please. To understand stars well, you must find out how much matter stars contain. That is, their masses. Do they all contain about the same mass as the Sun? Or are some more massive and others less? How do you think? Unfortunately, it is difficult to determine the mass of a star. Looking through a telescope, you see only a point of light that reveals nothing about the mass of the star. Gravity is the key. Matter produces a gravitational field, and you can figure out how much matter a star contains if you watch another object move through the star's gravitational field. To find the masses of stars, you must study binary stars, two stars that orbit each other. The key to finding the mass of a binary star is undertaking orbital motion. Previous semester illustrated orbital motion by asking you to imagine a cannonball fired from a high mountain. If Earth's gravity didn't act on the cannonball, it would follow a straight line path and leave Earth forever. Because Earth's gravity pulls it away from its straight line path. The cannonball follows a curved path around Earth, an orbit. When two stars orbit each other, then Martial gravitation pulls them away from the straight line path and makes them follow closed orbits around a point between the stars. Each star is a binary system, moves in its own orbit around the system's center of mass, the balance points of the system. If the stars were connected by a massless rod and placed in a uniform gravitational field, such as the near-Earth surface, the system would balance at its center of mass, like a child's seesaw. Okay? If one star is more massive than its companion, then the more massive star is closer to the center of mass and travels in a smaller orbit, while the lower mass star whips around in a larger orbit, as you can see from this slide. The ratio of the masses of the mass ma over mb equals Ra over Rb, and the inverse of the ratio of the radii of the orbits. If one star has an orbit twice as large as the other star's orbit, then it must be half as massive. Getting the ratio of the masses is easy, but that doesn't tell you the individual masses of the stars, which is what you really want to know. That takes further analysis. To find the mass of a binary star system, you must know the size of the orbits and the orbital period, the length of time the stars take to complete one orbit. The smaller the orbits are, and the shorter the orbital period is, the stronger the star's gravity must be to hold each other in orbit. For example, if two stars whirl rapidly around each other in small orbits, then their gravity must be very strong to prevent their flying apart. Such stars would have to be very massive, from the size of the orbits and the orbital period. You can figure out how much mass the stars contain, as explained in the slide Reasoning with Numbers. Such calculations yield the total mass, which combined with the ratio of the masses found from the relative sizes of the orbits, can tell you the individual masses of the stars. Actually, figuring out the mass of a binary star system is not easy as it might seem from this discussion. The orbits of the two stars may be elliptical, and also the orbits lie in the same plane. That plane can be tipped at an unknown angle to your line of sight, and further distorting the observed shapes of the orbits. Astronomers must find a way to correct for these distortions. In addition, astronomers analyzing binary systems must find the distances to them so they can estimate the true size of the orbits in astronomical units. Finding the masses of binary stars requires a number of steps to get from what you can observe to what you really want to know, the masses. Constructing such sequences of steps is an important part of science. Also, there are many different kinds of binary stars. Three types are especially useful for determining stellar masses. These are discussed separately in the next part of our lecture. In a visual binary system, the two stars are separately visible in the telescope. Only a pair of stars with large orbits can be separated visually. If the orbits are small, the telescope cannot resolve the star images, and you see only a single point of light. In a visual binary system, you can see each star moving around its orbit. Visual binary systems are common. More than half of all stars are members of binary star systems, and many of those are visual binaries. Favorite star Polaris has two stellar companions. Few visual binaries, however, can be analyzed completely. Many are so far apart that their periods are much too long for practical mapping of their orbits. Others are so close together that they are hardly visible as separate stars, and it is difficult to map the shape of their orbits. One of the stars that orbit Polaris, for instance, orbits with a period over 1,000 years, and the other is so close to Polaris that is hardly visible even with the Hubble Space Telescope. Astronomers study visual binary systems by measuring the position of the two stars directly at the telescope or in images. In either case, the astronomers need measurements over many years to map the orbits. The first frame of this slide shows a photograph of our favorite star Sirius, which is a visual binary system made up of the bright star Sirius A and its white dwarf companion Sirius B. The photo was taken in 1960. Successive frames in next figures show the motion of the two stars as observed since 1960 and the orbits the stars follow. The orbital period is 50 years, and astronomers have found accurate masses for both stars. If the stars in a binary system are close together, the telescope, limited by diffraction and seeing, reveals only a single point of light. Only by looking at a spectrum, which is formed by light from both stars and contains spectral lines from both, can astronomers say that there are two stars present and not one. Such a system is a spectroscopic binary system. And this figure shows a sequence of spectra recorded over a few days as the stars in a spectroscopic binary moved around their orbits. You can see how the spectral line in the top spectrum splits into two components that are move together, merge as they cross, and then move apart again. This is a true sign of a spectroscopic binary. To understand the spectra in this figure, look at the diagrams in this figure, which shows two stars orbiting each other. In the first frame, star A is approaching while star B recedes. In the spectrum, you see a spectral line from star A Doppler shifted towards the blue end of the spectrum, while the same spectral line from star B is Doppler shifted towards the red end of the spectrum. As you watch the two stars revolve around their orbits, and they alternatively approach and recede, and you see small Doppler shifts moving with spectral lines apart, and then back together. In a real spectroscopic binary, you can't see the individual stars, but the sight of pair of spectral lines moving back and forth across each other, and would alert you that you were observing a spectroscopic binary system. At first glance, it seems that it should be easy to find the masses of the stars in a spectroscopic binary. You can find the orbital period by waiting to see how long it takes for the spectral lines to return to their starting points. You can measure the size of the Doppler shifts to find the orbital velocities of the two stars. If you multiply velocity times orbital period, you can find the circumference of the orbit, and from that, you can find the radius of the orbit. Now that you know the orbital period and the size of the orbit, you should be able to calculate the mass. One important detail is missing, however. You don't know how much the orbits are inclined to your line of sight. Do you remember as we speaking a few minutes ago? So you can find the inclination of a visual binary system because you can see the shape of the orbits. In a spectroscopic binary system, However, you cannot see the individual stars, so more than half of all stars are in binary system. And most of those are spectroscopic binary systems. Many of the familiar stars in the sky are actually pairs of stars orbiting each other, as you may see from this slide. You might wonder what happens when the orbits of a spectroscopic binary system lie exactly edge on Earth. The result is the most informative kind of binary system. As mentioned earlier, the orbits of the two stars in a binary system always lie in a single planet. If that plane is nearly edged onto Earth, then the stars appear to cross in front of each other. Imagine a model of a binary star system in which a cardboard disk represents the orbital plane and balls represent the stars as in this figure. If you see the model from the edge, then the balls that represent the stars can move in front of each other as they follow their orbit. The small star crosses in front of the large star, and then, half an orbit later, the large star crosses in front of the small star. When one star moves in front of the other, and it blocks some of the light, and the star is eclipsed. Such a system is called an eclipsing binary system. Seen from the Earth, the two stars are not visible separately. The system looks like a single point of light. But when one star moves in front of the other star, part of the light is blocked, and the total brightness of the point of light decreases. And this figure shows a smaller star moving in an orbit around a larger star. First eclipsing the larger star, and then being eclipsed itself as it moves behind its companion. The resulting variation in the brightness of the system is shown as a graph of brightness versus time, a light curve. Remember, you can't see the individual stars in an elliptical system. Cover the stars in this figure with your fingers and look only at the light curves. If you saw such a light curve, you would immediately recognize the point of light in the sky as an eclipsing binary system. The light curves of eclipsing binary systems contain tremendous amount of information, but the curves can be difficult to analyze. This slide shows only an idealized system. Compare with this figure, which shows the light curve of a real system in which the stars have dark spots on their surfaces and are so close to each other that their shapes are distorted. Once the light curve of an eclipsing binary system has been accurately observed, you can construct a chain of inference leading to the masses of the two stars. You can find the orbital period easily, and you can get spectra showing the Doppler shifts of the two stars. You can find the orbital velocity because you don't have to until the orbits. You know they are nearly edge-on, or there would not be eclipses. Then you can find the size of the orbits and the masses of the stars. Earlier in our lecture, you used luminosity and temperature to find the radii of stars. But eclipsing binary systems provide a way to measure the sizes of stars directly. From the light curve you can tell how long it took for the small star to cross the large star. Multiplying this time interval by the orbiting velocity of a small star gives the diameter of the larger star. You can also determine the diameter of the small star by noting how long it took to disappear behind the edge of the large star. Okay? Nice. For example, if it took 300 seconds for the small star to disappear while traveling 500 kilometers per second relative to the large star, then it must be 150,000 kilometers in diameter. Of course, there are complications due to the inclination and its eccentricity of orbits, but often then effects can be considered. Algol, or Beta Persei, is one of the best known eclipsing binaries because its eclipses are visible to the naked eye. Normally its magnitude is about 2.15, but its brightness drops to 3.4 during eclipses that occur every 68.8 hours. Also, the nature of the star was not recognized until 1783. Its periodic dimming was probably known to the ancients. Algol comes from the Arabic for the Timon, and it is associated in constellation mythology with the serped head of Medusa, the sight of whose serpentine locks tuned mortals to stone, as you can see from this slide. Indeed, in some accounts, Algol is the winking eye of the Timon. From the study of binary stars, astronomers have found that the masses of stars range from roughly 0.1 solar masses at the low end to nearly 100 solar masses at the high end. The most massive stars ever found in a binary system have masses of 116 and 89 solar masses. A few other stars are believed to be more massive, 100 solar masses to 150 solar masses, but they do not lie in binary systems, so astronomers must estimate their masses. When you look at the light curve for an eclipsing binary system with total eclipses, how can you tell which star is hotter? Scientists must have good imagination to visualize objects they cannot see. This scientific argument will exercise your imagination. If you assume that the two stars in an eclipsing binary system are not the same size, then you can refer to them as the largest star and the smallest star. And when the smallest star moves behind the largest star, you lose the light coming from the total area of a small star. And when the smallest star moves in front of the largest star, it blocks off light from the same amount of area on the largest star. In both cases, the same amount of area, the same number of square meters, is hidden from your sight. Then, the amount of light lost during the eclipse depends only on the temperature of the hidden surface. Because temperature is what determines how much a single square meter can radiate per second. When the surface of the hottest star is hidden, the brightness will fall dramatically. But when the surface of the coolest star is hidden, the brightness will not fall as much. So you can look at the light curve and point to the deeper of the two eclipses and say, that is where the hottest star is, behind the coolest star. Now change the argument to consider the diameters of the stars. How could you look at the light curve of an ecliptic binary with total eclipses and find the ratio of the diameters? Try to find this answer himself, and let's discuss it during our next lecture. Okay? So I think it's enough for today. As usually, any questions or propositions? I hope you enjoyed this lecture, and I'm looking forward to seeing you next time. Bye.